Good day. I am Krishagay Lumayag Alpad, BSIT 1B. My topic is all about basic probability rules. Probability is obtained by dividing the number of possible ways of achieving the desired event by the total number of possible events. Since the total number of events is always equal to or larger than the desired event, probabilities are always a number between 0 and 1. How to solve a probability word problem? We follow the following steps for solving a given word problem in probability. The first step is to identify the experiment and the events for which we have to find the probability. Now, find out the number of outcomes of the experiments and every event that is determined in step 1. Find the probability of all events determined in step 1 using values obtained in step 2. Use probability laws to find the required probability as and when required, like a multiplication rule, Bayes' theorem, addition rules, etc. Independent events probability. An event which remains unaffected by previous event or set of events is known as an independent event. For example, tossing a coin is an independent event as each time the coin is being tossed, the result will be independent of the previous toss. If A and B are independent events, then the probability of both the events happening will be P open and close parentheses A and B is equals P open and close parentheses A, and P is open and close parentheses B, and P is open and close parentheses A and B is equals to P open and close parentheses A and P open and close parentheses B. That is the product of the probability of each event. Examples: a coin is being tossed twice. Find the probability of getting both heads. Solution: probability of getting a head in one toss is equals to 0.5. Probability of getting a head in second toss is 0.5. Probability of getting both heads is equals to 0.5 times 0.5 is equals to 0.250. 0.5 times 0.5 is equals to 0.25. In words, we say that the events are mutually independent if the simultaneous occurrence probability of any finite number of the events is same as the product of the respective probabilities. Next examples. A basket contains 3 orange, 5 apples, and 2 peaches, and 4 fruits are drawn one after another with replacement. Then find the probability that none of the chance we got an orange. Solution: let E1, E2, E3, and E4 be the events of not getting an orange in first, second, third, and fourth pick respectively. Since every pick is done after replacement, thus the events E1, E2, E3, and E4 are independent events. Also, P open and close parentheses E1 is equals to P open and close parentheses E2 is equals to P open and close parentheses E3 is equals to P open and close parentheses A4. Since there are 7 fruits apart from orange, so P is open and close parentheses E1 is equals to 7 over 10. So the required probability is given by P open and close parentheses E1 intersection to E2 intersection to E3 intersection to E4 is equals to P open and close parentheses A1 P is close open and close parentheses E2 P open and close parentheses E3 P open and close parentheses E4 is equals to open and close parentheses 7 over 10 squared. So these are the 3 definitions of probability. 1. Theoretical or classical definitions of probability. Number 2. Empirical or statistical definitions of probability. Number 3. Axiomatic definitions of probability. Theoretical or classical definitions of probability. Let a random experiment produce only a finite number of mutually exclusive and equally likely outcomes. Then the probability of an event A is defined as P, open and close parentheses, is equals to a number of favorable outcomes to A over total numbers of outcomes. Theoretical probability is also known as classical or a priori probability. Classical probability is also known as statistical probability. So for examples, consider the experiment of tossing a coin. What is the probability of getting a tail? Solutions. Probability of an event A is given by P, open and close parentheses, is equals to a number of favorable outcomes to A over total number of outcomes. The sample space of the experiment of tossing a coin is given by S is equals to head, tail. Number of favorable outcomes to tail is number 1. Total number of outcomes is number 2. So P getting a tail is equals to 1 over 2. Is equals to 1 over 2. So another examples. An yarn contains 6 green, 3 white, 2 blue, and 1 red balls. If a ball is picked, then find the probability that ball is 1 red in color, 2 either blue or white in color, 3 not all green in color. Solution. Here is equals to 12. All the outcomes are equally likely to occur. Favorable outcomes for a red ball is equals to 1, hence P red is equals to 1 over 12. Favorable outcomes for blue ball is equals to 2. Favorable outcomes for white ball is equals to 3. Hence, P blue or white is equals to P blue plus P white is equals to 2 over 12 plus 3 over 12 is equals to 5 over 12. Favorable outcomes for green ball is equals to number 6. So, P green is equals to 6 over 12 is equals to 1 over 2. Hence, P not green is equals to 1 minus P green is equals to 1 minus 1 over 2 is equals to 1 over 2. Next is the empirical definitions of probability. Empirical probability of an event is estimate that the event will occur based on the ample data of performing repeated drills of probability experiment. The empirical approach to probability is based on the law of large numbers. So to achieve more accuracy in the result, collect more observations which provide more accurate estimate of the probability. Empirical probability is also known as experimental probability. The empirical probability gives the likelihood of the events to happen based on the outcomes from a set of previous experiments. It is different from theoretical probability as empirical probability is independent on the occurrence of events is a collected data. Empirical probability formula. Probability of an event happening is the ratio of the time similar events happened in the past. Empirical probability number of times events occurs over total numbers of times experiment performed. So formula. Empirical probability of event EPE is equals to total number of occurrence of E over total number of experiments. Illustrative examples. Number 1. 8 coins are tossed. Below are frequencies of the numbers of tails which appeared. XF. X is 0, 1, 2, 3, 4, 5, 6, 7, 8. F 2, 15, 29, 57, 70, 59, 20, 10, and 8. Calculate the probability of occurred tails. Equal to 5, less than 4, and more than 6. Solution. Total number of heads occurred is an experiment is equals to 2 plus 15 plus 29 plus 57 plus 70 plus 59 plus 20 plus 10 plus 8 is equals to 270. P, open and close parentheses, occurred tails equal to 5. From given table, number of required cases is equals to 59. Therefore, P tails equals to 5 is equals to 59 over 270 is equals to 0.22. Occurred tails less than 4 from given data, number of favorable cases is equals to 2 plus 15 plus 29 plus 57 is equals to 103. Therefore, P open and close parenthesis tails less than 4 is equals to 103 over 270 is equals to 0.38. P more than 6 tails. Total number of cases is equals to 10 plus 8 is equals to 18. So P tails more than 6 is equals to 18 over 270 is equals to 0.7. Another examples. The following are the marks obtained by 1,200 students in a particular examinations. So marks and number of students. Marks is 1 to 120, 120 to 140, 140 to 160, 160 to 180, 180 to 200. Number of students 63, 142, 500, 320, and 170. Find the probability that a student selected has marks under 140, above 180, between 140 and 200. Solution. Total marks obtained by students is equals to 63 plus 142 plus 500 plus 320 plus 175 is equals to 1,200. Probability that a selected students get marks under 140. There are 63 plus 142 is equals to 205 students. P students scored marks under 140 is equals to 205 over 1,200 is equals to 0.17. Probability that a selected students get marks above 180. There are 175 students. P students scored marks above 180 is equals to 175 over 1,200 is equals to 0.15. Probability that a selected students get marks between 140 and 200, there are 500 plus 320 plus 175 is equals to 995 students. P students scored marks between 140 and 200 is equals to 995 over 1,200 is equals to 0.83. Number 3. A coin is thrown 100 times, out of which heads appears 12 times. Find the experimental probability of getting a head. Solution. The coin is thrown 100 times, so total number of tails is equals to 100. Given head occurs 12 times, so the total numbers of times the required event occurs is equals to 12. Therefore, probability of getting the event of head is equals to 2 over 100. 12 over 100 is equals to 0.12 using experimental probability formula. So last is axiomatic definitions of probability. Let S be the sample space of a random experiment. Let A be an event of a random experiment. According to these definitions, probability of an event is a real number which satisfies three axioms. Number 1, axiom PA less than equal 0. Number 2, axioms 2, PS is equals to 3. Number 3, axiom P union B is equals to PA plus PB, where A and B are disjoint events. Therefore, PA is a real-valued, non-negative, totally additive set functions. Therefore, PA is a measure and it is the probability of A. Axiomatic definitions is usually not used to work out problems. Properties of probability. The probability of an event is always greater than or equal to 0. The probability of an event lies between 0 and 1. Probability of an impossible event is 0. That is, P0 is equals to 0. Probability of a sure event is number 1. That is, PS is equals to number 1. Mutually exclusive events. A set of outcomes is referred to as event. When two events cannot occur at the same time, then we say that the events are mutually exclusive, else the events are said to be not mutually exclusive. For example, when we flip a coin, then either heads can come or tails. Both heads and tails cannot be outcomes simultaneously. Example of not mutually exclusive events is the event of getting a total of number 5 or getting prime numbers on top in the experiment of throwing a pair of dice. Formula. There are two things that are clear when we say two events C, M, and N that are associated when an experiment are mutually exclusive. Number 1, M and N. The intersection set is equal to null and hence P, M, and N is equal to 0.0. This is because when the events cannot occur simultaneously, there can be nothing in common in them. Number 2, M or N. PM or N is equal to PM plus PN. The probability of union of two mutually exclusive events is given by the sum of the probabilities of the events individually.